Greetings from Hunter College. My name is Abono Berry, and welcome to lecture number 15. We're just going to make today setting up the proof by defining compactness and open covers. Heine-Borel, Heine was a German mathematician who was mostly known for real analysis, and Borel was a mathematician and politician who was more known for probability and measure theory. But that's not really what matters today. What matters today is figuring out what the Heine-Borel theorem is. So what is the Heine-Borel theorem? Well, it's very easy to state, but pretty difficult to prove.
Is this a part 1, part 2, or part 3?
We'll be doing it in 3 parts. So here we want to prove that 3 statements are equivalent. So, first, you have statement number 1. The set S is, the set S in the real numbers is closed and bounded. Number 2, a set S is sequentially compact. The order we're going in is proving 1 is equivalent to 2, or rather that 1 implies 2, then that 2 implies 3, or rather that 3 implies 2, and then we're going to use both 1 and 2 and show that together they imply 3. That completes the full circle. So, today we're going to be doing this part, showing that 3 implies 2. So, we're showing that a set S is covering compact if a set S is sequentially compact. So, to do that, we first have to figure out what it means to be sequentially compact and what it means to be covering compact. So, these are essentially 2 different definitions for the same thing, but we can only figure out that they're the same thing by proving this. So, to be sequentially compact essentially means that if we have a set S, then for all sequences, let's say lowercase s k in S, there exists a convergent, or let's call it Sn, there exists a convergent subsequence lowercase s sub n sub k whose limit is also in S. So essentially, for all sequences that use elements of S, there exists a convergent subsequence in them by the Bolzano-Weierstrass theorem, and that subsequence's limit is also in S. So, then, what does it mean to be covering compact? We have to use all the space we can. Can't waste. So, what does it mean to be covering compact? Well, that just means that every open cover has a finite subcover. But wait, we never even find cover and subcover to begin with. What are these? Well, they're exactly what they say they are. Let's say we have a set S, which is just this interval from A to B. This is our set S. So now, what would you imagine a cover would be for this set? Well, what does it mean to cover something? Well, I mean, if a blanket is covering someone's body, then that means that it fully goes over their body. So, like this, it's fully going over their entire body, while it also has some extras, some redundant parts. So, in the same way, an open cover is any union of open sets, which itself will be an open set by the theorem that we proved a while ago, I think 2 lectures ago. Union of open sets that includes S. So, for example, what would an open subcover of the set 0, 1 exclusive be? So that's just this set right over here. So what would an open subcover be? Well, an open subcover could be, for example, a finite one. An open cover could be a finite one. For example, one open cover could be the set -1 to 2. And it has to be open, by the way. Another one could be, let's think about it. Since the union of open sets is always open, could be minus 0.5 to 0.5, and then 0 to 1. Yes, I know, technically the whole interval is right over here. So, I mean, this also completely covers the interval. Now, this is something pretty easy to think about. Just a finite union of sets. Now, we know that an infinite union of open sets is also an open set. So, if we have O lambda such that lambda is in capital lambda, then we know, and capital lambda could be finite or infinite. That's why we're not using n or r or anything arbitrary like that. So then we can have lambda, all lambda in lambda. Don't want to start off with lambda equals 1 or something, because 1 might not be in lambda. So this fully contains our set. And I think we're actually calling it S, sorry. So, what would it be like for lambda to be infinite? An infinite covering of sets. Well, let's imagine an example. One example I can think of on the spot is 1 to 1/3, then 1/2 to 1/4, then 1/3 to 1/5, then 1/4 to 1/6, then 1/5 to 1/7, and so on and so forth. So it's just the union for all k in the natural numbers of 1 over k to 1 over k plus 2. And of course, there's some redundancy. There's some overlap. So if we have 0, 1 right over here, we can see the redundancy and the overlap. We go from 1 to 1/3. There's an interval right here. Then, let me grab my red marker. we go from 1/2 to 1/4. And already you can see we've got a huge amount of overlap. This huge redundant chunk. 1/3 to 1/4, this little 1/12 part. And then we have 1/3 to 1/5, which is even more overlap. So this entire thing is overlapped now. And this just keeps growing and growing and growing. But here's the thing. This is technically not redundant. Why? Well, let's take a look at an example of a redundant open cover to understand just exactly why. So it would be the union for all k in the natural numbers of the intervals minus k to k. Change the whole thing, right? Because we have the number line over here, and this is 0 to 1. Then our first interval is going to be just like so. Okay, already contains it. The second interval is going to be even more wide. Okay, the third interval is going to be even more wide than the fourth one, and so on and so forth. So, of course, this is a union of open sets, very clearly, and the sets, since they're nested, they all contain our interval. But it's redundant. You want to know why? We can find a finite subcover. Now you might say, well, that means that we can remove a few, right? Like, for example, remove this one, it still sticks. This one, and it still sticks, so on and so forth. But we can do the same thing here, right? We can remove this one, and it's still a subcover, an open cover. Sorry. A lot of sets here are completely, entirely redundant. So, yeah, like I can remove this one, and it's still a cover, because 1/3 to 1/5 already provides that missing 1/3 to 1/4 thing that we were looking for earlier. So does that 1/4 to 1/6 and 1/5 to 1/7. So what's the difference between these two? Well, the thing is, we can remove finitely many from this one, and we can still have enough, but we can remove infinitely many from this one and still have enough. We can remove literally every single thing except the first interval minus 1 to 1, still an open cover. Why? Because minus 1 to 1 is a finite subcover. Essentially, if we take it to be lambda in lambda O lambda, then we can find, oh, this is intersection sign, sorry. Then we can find, oh my gosh, have I been writing the intersection sign everywhere? I must look so dumb. Oops. Okay. So, you have a subcover, which is essentially just a subset of our set of sets. Yeah, I know, that sounds confusing. So, essentially, we have O n lambda, or something in that vein. How could I illustrate this better? Oh, yes. So, we could have n in the naturals, O lambda n. So, it will be specific numbers from our set capital lambda, but it's not going to be all of them. So, in this case, we have only one of them. And the difference is, this is not a union of infinitely many sets. It's a union of only finitely many. and yet it still manages to cover the whole thing. You cannot find a union of only finitely many of these that covers the whole thing, right? Yeah, no, you can't. So, that's why none of these are redundant, while almost all of these are redundant. So now we know what a cover and a subcover is, but we haven't even gotten to the start of the proof yet. So we need to prove that something that's sequentially compact is also covering compact.